Input validation and output encoding exist to protect software at its most vulnerable points, where untrusted or malformed data crosses a boundary into trusted logic. Every application accepts input in some form, whether from users, other systems, files, or automated processes, and that input cannot be assumed to be well-formed or benign. Many of the most damaging vulnerabilities arise not from complex logic errors, but from simple assumptions about what data will look like. Validation and encoding are therefore foundational controls because they constrain how data is interpreted before it can influence behavior. When these controls are applied consistently, they turn unpredictable external input into predictable internal data. Before we continue, a quick note. This audio course is a companion to the CISS books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Input validation is the practice of checking incoming data to ensure it meets explicit expectations before it is processed. These checks typically include data type, length, format, and allowed characters, because each of these dimensions can be abused if left unconstrained. A numeric field that accepts text, or a short field that accepts unbounded input, creates opportunity for overflow, injection, or logic bypass. Validation should be explicit rather than implicit, meaning the code should clearly state what is acceptable instead of relying on downstream failures. When validation is precise, invalid input is rejected early, reducing both risk and complexity deeper in the application. Allow list validation is a more robust approach than attempting to block known bad values, because it defines what is acceptable instead of trying to anticipate everything that is dangerous. Block lists fail over time because attackers invent new encodings, separators, and payloads that were not considered originally. An allow list constrains input to a known safe set, such as specific formats, enumerated values, or tightly defined patterns. This approach aligns with secure defaults because anything not explicitly permitted is rejected. While allow lists require more careful design up front, they are far more resilient to change and creativity from attackers. Canonicalization is an important supporting concept because input can be encoded in multiple ways that appear different but represent the same underlying value. Without canonicalization, validation checks can be bypassed by presenting data in an unexpected encoding that is normalized later by the system. Resolving input into a standard form before applying validation ensures that checks are applied to what the system will actually process. This includes decoding %encoded characters, Unicode representations, or alternate path separators. Canonicalization reduces ambiguity and ensures validation logic aligns with real execution paths. Server-side validation is mandatory even when client-side validation exists, because client-side checks are advisory rather than authoritative. Client-side validation improves user experience by catching errors early, but it cannot be trusted to enforce security. Attackers can bypass or manipulate client logic easily, submitting requests directly to back-end services. Server-side validation is the final gate that determines whether input is accepted or rejected. Relying solely on client-side checks creates a false sense of safety that collapses under minimal adversarial pressure. Output encoding addresses a different but equally important boundary, where internal data is rendered into an output context that could interpret it as executable code. Even well-validated input can become dangerous if it is output incorrectly. Output encoding ensures that data is treated as data, not as instructions, when rendered in user interfaces, scripts, or queries. This control is especially critical for preventing injection attacks, where attacker-supplied content is executed by the receiving environment. Proper encoding preserves meaning while neutralizing special characters that would otherwise alter behavior. Contextual encoding matters because different output contexts interpret characters differently. Encoding suitable for a hypertext markup language context may be unsafe in a script context, and vice versa. Uniform encoding applied everywhere often fails because it does not respect these differences. Secure handling requires encoding that is specific to where the data will appear, whether that is markup, script, uniform resource locator parameters, or database queries. Understanding context is therefore essential because the same data can be safe in one place and dangerous in another. Database interactions deserve particular attention because improperly handled input can alter query logic directly. Parameterized queries address this risk by separating data from instructions, ensuring that user-supplied values cannot change the structure of a query. This approach removes the need for complex escaping rules that are easy to misuse. When parameters are used correctly, the database treats input strictly as values rather than executable fragments. This separation is one of the most reliable defenses against injection in data stores. Validation must also apply to less obvious input types, such as files, metadata, and structured formats. Uploaded files should be checked for size, type, and content rather than relying on file extensions alone. Metadata fields can be abused to carry unexpected payloads if they are not validated explicitly. Structured formats like JavaScript object notation still require validation of schema, field types, and allowed values. Treating structured input as inherently safe is a common mistake that leads to parsing and logic errors. Error handling interacts closely with validation because the way errors are reported can either protect or expose internal details. When validation fails, error messages should explain the issue in a user-appropriate way without revealing system internals. Detailed diagnostic information belongs in internal logs, not in external responses. Excessive detail in error messages can provide attackers with information about validation rules, database structure, or application logic. Controlled error handling ensures validation failures do not become information disclosure vulnerabilities. Normalization is closely related to canonicalization and reinforces validation by reducing variation in how input is represented. Different separators, whitespace, or encoding schemes can allow equivalent values to bypass checks if they are not normalized consistently. By reducing input to a normalized form, applications eliminate many subtle bypass techniques. Normalization should occur before validation and be applied consistently across all entry points. When normalization is inconsistent, attackers search for the one path where it is missing. Logging invalid input can support detection and analysis by revealing patterns of probing or attack. Repeated validation failures may indicate attempted exploitation rather than user error. However, logging must be done carefully to avoid capturing sensitive data or attacker payloads that create new risk. Logs should record the fact of rejection and relevant context without storing raw, untrusted content unnecessarily. When balanced correctly, logging supports security monitoring without becoming a liability. Using well-tested secure libraries reduces the likelihood of custom parsing errors and inconsistent encoding behavior. Writing custom validation and encoding logic is error-prone, especially across multiple contexts and data types. Mature libraries encapsulate correct behavior, edge case handling, and updates as standards evolve.
Standardizing on approved libraries also improves consistency across teams and services. This reduces cognitive load and makes reviews and testing more effective.
Input validation and output encoding ultimately protect the boundaries where untrusted data enters and leaves trusted execution. These controls assume that data can be hostile, malformed, or unexpected, and they design for that reality rather than hoping it does not occur. Validation constrains what is accepted, while encoding constrains how accepted data is interpreted. Together, they prevent entire classes of vulnerabilities that recur across languages and platforms. When applied systematically, they turn data handling from a frequent source of weakness into a reliable line of defense.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.